Alrighty. Good evening, guys. Can you all hear me?
Yes, good evening, Professor.
Are there any questions or comments before we get started on tonight's lecture? Okay, if that's not the case, then we are working on Brownian motion. This is what we're going to introduce last time, and we're going to continue looking at Brownian motion tonight. And it's just recall. So recall that this object here, this is a Brownian motion. Quite often it's also called the Wiener process. So the letter B comes from the word Brownian, but you'll also very often see this as a capital W, and it comes from the word Wiener process. This is a Brownian motion. This is a collection of random variables. This is a Brownian motion if a number of properties hold. So just often normalize the Brownian motion to start out when, so that t down here, this is our time variable. So when when time is equal to 0, so the initial point is just normalized to be 0, and often yeah, maybe we can talk about how to change that in a little bit. The other assumption is that if I take a path, so for any omega in my sample space, it's true that the map, so t is positive, so it goes from 0 to infinity. When I map t into bt of omega, this is a continuous function. So those are the path properties. And then we also have the distributional properties. We are saying that bt minus bs, this is going to be standard normal. And we are saying that we have independence. So if I take non-overlapping intervals, just maybe put them like this. So take non-overlapping intervals, I'll have then that btn minus btn minus 1 is independent of btn minus 1 minus btn minus 2, which is independent, and all the way down to b at t1 minus bt0. So I have all these properties. So that's my Brownian motion. Maybe some of you have heard about a maybe it's just a side remark. you could replace 3. You could replace 3 by saying that BT minus BS would be Poisson distributed with some parameter lambda. And you could replace 2 by saying that instead of continuous, you could have the word right continuous. And if you do that, then you get a Poisson process, which some of you probably come across. So you can see you can play with this distributional property here that you have normality. You could put in something else like a Poisson distribution, or you could even keep it more general if you so desire. We're not in this course. We're not going to be playing with the Poisson process, but if you're so inclined, if you flip over towards the end of the textbook, the last chapter in there's a chapter about the Poisson process. So it discusses how all these sections in the first part of the book, how they have to be changed to accommodate that instead of normality, you have this Poisson distribution. There are some things to observe here. If I take in this formula, if I take S to be 0, then I get a 0 here. Right? So BT becomes normally distributed mean 0 and variance T. So let me just try to highlight that. So in particular, so because BT is normally distributed mean 0 and variance T, we'll have, I can compute the expectation of, say, the absolute value of BT. So how would I go about doing that? Well, I'll write out here. I would write out. I want something that is standard, normally distributed. So how will I do that? I'll do something like, how do I get a standard normally distribution? Well, I need to get rid of this, make this a 1. So I'll take BT and then divide by, what should I divide by?
T.
Is that right? If I want something that is standard normal, should I divide by T or should I divide by something else?
Should it be T squared?
Yes.
Yeah.
Yep. Right. So I'll do this, and then I have to multiply onto the square root anyway. And then what? So now I have a standard normal in here. I have a standard normal in here, so I can keep my square root T outside. And then I'll plug in an integral over R. And now I'm computing the absolute value of a standard normal. So I need an absolute value here. I need 1 over root 2 pi e to the minus x squared over 2 dx. And then I can see there's something with symmetry in here. This is a symmetric function, so I can write this as 2 times root t, an integral from 0 to infinity, and then an x, and then I have this root 2 pi e to the minus x squared over 2 dx. Well, I think I can find, because I have an x here, I can write this here as 2 root t 2 pi root And then what? I'll have minus, or e to the minus x squared divided by 2. If I take the derivative of this function, I'll get this minus down, it'll cancel. I'll get x squared divided by 2. That's going to give me that x up here. So that looks good. And then in here, I have to have x equal to 0. I have x equal to infinity. Okay, so what do we end up with here? I'm going to put in infinity here, I'm going to get a 0, and then I'm going to get a 0 that's going to be a 1 with a minus and a minus. So I'm left here with 2 root t over 2 pi root. So what does that tell me? Well, I want to see how bt behaves as a function of t. So maybe I can do something like maybe I can just recall an inequality from probability called Chebyshev's. Can I spell Chebyshev? Chebyshev's inequality. Instead of remembering Chebyshev's inequality, it's not too hard to derive. So if I take a random variable and take an absolute value of it, then what I can do is this is positive. So if I pick an epsilon, if I pick an epsilon bigger than 0, then I can write the absolute value of x times the indicator that x is bigger than epsilon. If I take expectation over on the right hand side, right, this is going to give me a 0 here when the absolute value of x is small. Right, so what I have here on the right hand side, this is smaller. And so again, I can bound this thing from below, because if I put in epsilon instead of that thing, I'm going to get something that's even smaller. So here we'll have an epsilon. And then an expectation of an indicator. This is the same thing as the probability that the absolute value of x is bigger than epsilon. And so we get Chebyshev's inequality, which says that the probability that a random variable absolute value is bigger than some number, it has an upper bound of 1 over epsilon, divide epsilon over on the other side, and then the expectation of x. So I'm hoping that most of you have seen Chebyshev's inequality before. If not, here's an outline of its proof. So if I didn't combine, so we can combine Chebyshev and this expectation being 2 root t over 2 pi 2 root 2 pi to get a version of what's called the law of the iterated logarithm. So this is a weak form, but nevertheless, it's going to be good enough for what I want to show you tonight. And so here it goes. We're interested in the probability that the absolute value of bt divided by t is bigger than epsilon. Okay, so I can move the t to the other side. This is bigger than epsilon t. Then I can use Chebyshev. And says that this probability, I have the absolute value bt, this is less than the constant, 1 over the constant. So here the constant is epsilon t times the expectation of the absolute value bt, which is the thing that I computed, so I can plug that in. And the thing to note here is that you have a root t up here, and you have a t here. So they combine nicely. I get 2 divided by, well, we have a square root of 2 pi, then you have an epsilon, and then there will be a square root t down here. And so what happens is that this thing here goes to 0. This goes to 0 as t goes up to plus infinity. So you can see here that when I'm looking at the absolute value of bt over t, when t gets to be bigger and bigger and bigger, chances that this is going to become bigger than epsilon is small. And so this has quite interesting implications. So there are non-trivial implications. For example, last time we looked at this ZT. Last time we looked at this object. Does anybody remember some of the properties that this particular stochastic process here has?
Is it a martingale?
Yeah.
And it had Markov.
It's a Markov. Okay, yeah. So I'm not interested in Markov right now, but it's also positive, right? And in particular, because it's a martingale, its expectation is equal to
ZT minus 1.
there's no conditioning here,
Oh, okay. That's true.
just an expectation. So martingales
Equal
Yeah.
to ZS.
Can you say that one more time?
Is that equal to ZS for martingale?
Yeah, but there's no S.
Oh, no conditional, right?
So this is equal to Z, C what?
Mm,
Martingales.
This remains ZT.
Yeah, the mean of CT, what is that equal to if you know CT is a martingale?
I mean, martingale is constant expectation, right?
So this is Z0.
Yeah.
And what is that equal to?
0.
Oh, no.
Oh, no, it's not a Brownian mode. Yeah.
No.
Equal to 1.
Yes.
But Y is equal to Z0.
This one?
Yes.
Well, because you know, because ZT is a martingale,
Mm-hmm.
you have for t bigger than s, you have the conditional expectation of ZT given if s is equal to ZS.
Yes.
And now use s equal to 0.
Oh, so if no conditional, it means S equal to 0?
Yeah, because Fs, this is the sigma algebra generated by Bu when U runs up to S. Right, so your F0, this is the sigma algebra generated by B0, but B0 is 0. So this is going to
Okay.
be your omega and the empty set. Right,
Mhm.
so when I condition on omega and the empty set, that conditional expectation, this is exactly the unconditional one.
Oh, okay.
So just make sure you get it straight here. This here is the martingale property. And the martingale property implies that you have constant expectation over time. We are not saying anything about the other implication. We're not saying anything at all about having constant expectation implying the martingale property. Any wild guesses why I am not saying anything about that? So what am I saying here? Is that,
Converse isn't true.
yes, that's probably why I'm not saying it, right, Richard? so this is something just to note, right? You have if mn or mt is a martingale, then that implies that the expectation of mt is equal to m0, right? So mt is a martingale, that implies it has constant expectation. This thing here, this is not true. This is not true. So let's do an example. If I take mt, if I take mt to be t times bt. So let's have a look. Does it have constant expectation over time? Let's test it out. E of mt is equal to E of t bt. And what is that equal to? Well, the t can go outside. And then I know B is a Brownian motion, right? So that's a martingale. And so B is a martingale, so it has constant expectation over time. This will be B0. And what is B0? That was 0. So this is a 0, which is equal to M0. So we have that. Now do we have this? Well, let's work out what the conditional expectation is. So now we go back to where was it? It was up here. So now we go back to this thing. We have to test that. So you take t bigger than s, and then you have mt given fs. And what is that equal to? Well, again, you plug in the definition. T bt given fs. T was a constant, so he hops outside. And now bt was a martingale. So the conditional expectation of bt given fs is equal to, well, we have the martingale property, so this is going to be
Yes.
bs. But this is That's not the same, right, as S times BS, which is UMS. So when you test for the martingale property, you really need to do this. It is insufficient just to test and see if it has constant expectation. That's not going to prove that it's a martingale. I forget who asked about. I forget who asked about these properties. Are there questions related to this sheet number 4 here? Okay, so let me just back up a little bit. I'm really interested in studying this stochastic process because it comes up this year is a Black-Scholes model. It doesn't look like it, but this is really a Black-Scholes model. That's why we're spending all this time on it, right? This is the Black-Scholes model. It has this particular exponential martingale. It's everywhere in the Black-Scholes model. So this is why we're spending all the time. We're spending so much time on this particular martingale. And so you have this property that it has constant expectation equal to 1, right? So in particular, from this, I can take the limit. I can send t to infinity. And if I send t to infinity, this is going to be 1. Because I'm taking the limit of a bunch of 1s. So if I have 1, 1, 1, 1, 1, 1, 1, and I take the limit is going to be 1. And what's funny about this example here is if I just tried to move this limit here inside, this is an exercise that we have played with before. Could I try to pull the limit inside here? So move him inside and see what you get. And this is where, yeah. Go ahead.
This is relating to like monotone convergence, right?
Yeah. So if you would have monotonicity, if it would be the case that if I had, right, so this is a big ask, right? So if with a bunch of lines underneath it, if the CT would be less than CT1 for all t less than or equal to T1, we could use monotone convergence. There's another theorem that says if you can find a big random variable, say a y, such that, well, first you need that CT is bounded from above by y, and second, you need that the expectation of y is finite. And then you can use, we could use what's called dominated convergence. It's called dominated because this y here is a big random variable, but it can unfortunately not be too big because right, there's no t dependence upon y. This here has to be true for any t that's positive. So you have this y that works for all t's at the same time, and it has this property that it has a finite interval. Then you can use the dominated convergence theorem. If you had this monotonicity, you could use monotone convergence. We don't have any of this. So we have neither. Because, and so here's the argument. What is the limit? How does this thing behave? If I look at the limit as t goes to infinity of ct. Yeah, so Rohan is asking, if it's monotone, we can put the limit inside. And so now I'm going to give an argument that's going to show that you cannot pull the limit inside. Well, let's write out what this here is. This would be the limit t goes to infinity of e to the bt minus 1/2 t. So it's not really clear what is happening here, but there's no, just to keep in mind here that there is no b infinity, and there's no limit as t goes to infinity of plus of bt. Okay, so you cannot write Brownian motion does not converge to anything at infinity. There's no b infinity. But we're claiming here that there's a limit here. So what's that limit? Well, what did we just do? We played quite a bit just before. If I took e to the bt and then I divided here by t, like that was the thing I knew would get small. So if I divide by t here, I have to put t outside. So I'll put a t here. And I'll have minus 1/2 here. Right, so what did I do? I took that t up here, put them outside a parentheses, a set of parentheses. So put t out here, put a parenthesis, divided by it. I don't have to worry about dividing by 0 here because t is a big number. And then we do the analysis. So bt over t, where does he go? Well, that was the analysis we roughly did, right? I know that, give me any epsilon, bt over t, it's gonna, the probability that this is bigger than any epsilon, right? Any epsilon strictly positive, that probability is going to go to 0. Right, so this ratio here, this thing is going to go to 0. Right, so this is going to go to 0. So overall, what's inside the parentheses is going to go to minus 1/2. And then I have a t outside. T is going to go off to plus infinity. So I have something that goes to minus 1/2 times something that goes to infinity. I put the two things together, I get something that converges to minus infinity. And then take the exponential function. The exponential function of something that goes to minus infinity is going to go to
1. Wait, hold on. Wait, will it not convert? Wait, if it exponential of something
going
like
to negative infinity. What would that be?
0?
Yes.
I have a question.
Yes.
Could we have like split the exponential to be e to the bt times e to the negative 1/2 t and seen that the e to the negative 1/2 t would have gone to 0, so then it wouldn't have mattered what e to the bt was?
But you don't have control over the first part. So I agree with, so let me write that in now. Your suggestion is to write this as EBT, e to the minus 1/2 t.
Yeah.
Yeah, so it's correct that this thing here, this is going to go to
0.
But what about this thing?
Does it? I guess my question is, does it matter if we know it's being multiplied by 0?
No. This one here, that is not true. So let me give you a counterexample. If I write, so we have a t here. So if I take t times 1 over t. 1 over t, where does he go?
To 0.
Mm-hmm. And where does the product go?
To 1.
Yes. So just because part of the product goes to 0, it doesn't mean that the product is going to go.
Right. Okay.
And then, so the problem that you're ending up with is you have something that approaches infinity, and you have something that approaches 0. When you take them, when you multiply these two things together, you can get all kind of things. And here it's worse because there is no, this thing here does not converge. This is just going to oscillate like crazy. So this one here doesn't have a limit, and it's, if you would have had a bound, like if you have something that oscillates like crazy, like a sine, like sine 1 over t, yeah, right, sine 1 over t, there's no, this doesn't have a limit as you go to, as t goes to 0, right?
Right.
This is just going to oscillate like crazy and crazy around 0, but it's bounded, right? It's bounded between -1 and 1. So for example, if you multiply this by 1 over t, because 1 over t is going to go to 0, and this thing here doesn't even have a limit, that product here is going to go to, but this doesn't have a limit. This thing here has a limit, and the limit of, I shouldn't say t, I should say, let me start over again. This is too little, right? So if you take xn times yn, if you're interested in this, what is the limit of this thing? And so you know two things. One, you know that xn is going to go to 0, and the second thing you know is that if I take absolute value of yn, I'm bounded by a constant k.
Right, then the whole thing goes to 0.
Yeah, then the whole thing goes to 0. Right? So for example, you could have xn being like 1 over n. You could have your yn being that sine I had before, sine over say 1 over
I've seen the example before with like you have the function x sine 1 over x, and then as x approaches 0, like as it gets closer to the origin, I think there's like a squeeze theorem thing where, because
that's what we're doing.
It's the same thing.
Just if you look at this example here, the yns is just sine n, right? So as a function of n, this here is going to oscillate between -1 and 1.
Oh, so we're doing sine n now instead of 1 over n.
Well, xn is 1 over n.
Okay.
I need the x's to go to 0, and I need the y's. I want to give an example where y is bounded by a constant, but yn does not have a, there's no limit for yn.
Gotcha. Yeah.
So this is exactly what happens here, right? Sinus of n, there's no, I cannot take the limit of yn here. There's no sine at infinity. But if I take the product between these two, you're good. This is going to go to 0. This thing here is going to go to 0 in this example. And it's exactly that sandwich theorem. Like I will take xn, yn minus its limit, that's a 0. This thing here is bounded by the constant times the absolute value of xn. And this is going to go to 0. It's this thing here that I'm assuming.
So was this argument for the fact that bt over t goes to 0?
No, there was a student that asked if I could do the splitting here. And what I'm saying is that.
Oh, okay. You're saying
about doing this.
If it was bounded, then you could.
If this was bounded, but it's not. This is not bounded. Right? It's bounded from below. EBT is bigger than 0, but there's no upper bound. There's no. It's not. There's nothing up there.
Yeah. Gotcha.
So I don't remember who asked the first question where we got into this discussion. Does this make sense to that student?
Yeah.
Okay. Yeah. So you can always do the splitting, but here you really need these two things to work together. And so you did work nicely together exactly here. And so now what you see is you cannot pull that limit inside, because if you pull this limit inside, you get a 0. Right? And 0 in expectation is not equal to 1. So what we get out of this calculation here is that the expectation of the limit of zt, well, this is 0, and this is strictly smaller than the limit of the expectations of ct, which is equal to 1. So you see, this is the argument for there's no monotonicity and there's no way you can use dominated convergence, because if you had such things, you would get that this is equal. And we don't have that. More questions, comments?
Yeah, I have a quick question. So how I remember you flipped back to like the what do you call it? The Chebyshev's inequality when we justified that BT over T was 0. I was a little
in the limit. Right, this is in the limit. This is as t goes to infinity.
right. The thing is like we have like, was it like a random variable over T?
Yes.
And we showed that this is the probability though of.
Yeah, so I am cheating a little bit here. So this is a good catch. So so what does it mean? What does it mean for BT divided by T to go to 0? So you see, I try to hedge a little bit here because I said this was a weak version. So the weakest type that you can come up with is what's called convergence in probability. So this is, you give me an epsilon, then the probability of BT over T being bigger than that epsilon, this is going to go to 0 as T goes to plus infinity. So that was the one we showed. So the one that you saw was almost sure. almost sure convergence. So this says that there exists a set omega prime. There exists, maybe I should just call it n. There exists an n. So let me write it like, if I take the limit of bt of omega over t, as t goes to plus infinity, this is equal to 0 for p almost surely. So that means that there exists a on the complement of this set of omegas where it doesn't converge. That complement has measure 0. So those are two notions, and they're not quite the same. Almost sure, this is the stronger one. This one here is the weaker one. We will actually also be using one that's called LP convergence. So LP convergence. This is as usual p equal to 1 and p equal to 2 that are the important ones. So that's the one where you say limit as t goes to infinity, and then you look at the expectation. It's not working so well for bt here, but you're looking for like a difference. Maybe I shouldn't call it t, maybe I should call it like xn. And then to this power p, so this is, so you'll say here that xn goes to x infinity. If I can look at the difference raised to the power p, compute that expectation and get a 0. So there are many different types of convergence. Here are 3 of them. And the one that I showed you, this is this weak version. That's the one that has to do with convergence and probability. And the one that I wrote down is almost sure. So I cheated, and you caught me. Right here, I am saying that this is almost surely. So so the upgrade to move into the actual law of the iterated logarithm, this is a little bit harder. A little bit. This is quite a bit harder. I'm not asking you guys to keep track of these various modes of convergence. As soon as you have these spaces where there are infinitely many different omegas, there are different kinds of convergence that you have to keep track of. There are a lot more than just these, the ones that you've seen here, but yeah. I don't know, Richard, did that help you or did it just make you more confused?
I think I understand there's some other concept that lets us conclude that it goes to 0. So that's fine.
Yeah. So the result that you see people use a lot is if say xn goes to x infinity in probability, right? So remember that's the definition that says that if you give me any epsilon, then when I look at the probability that xn minus x infinity is bigger than epsilon, that probability here converges to 0 as n goes to infinity. This does not imply that xn goes to x infinity almost surely, but it almost does. The precise statement is that there exists, you can find like, instead of xn, you can find like this xnk. Okay, so now we're shifting indices. This is a subsequence of your xn such that x and k goes to x infinity almost surely. So this is not true, but you can move into like a finer subsequence and then you can get it to work. And so for our purposes, this is good enough because I don't really care how the t's go to infinity. I'm just going to send them off to infinity. So this is a correct statement. So I can get through using this property here, but this is not obvious, and this is also something that would require a proof.
Gotcha.
Yeah, but if you're interested, you can look this up. You can lots of probability textbooks will discuss the relationship between these types of convergence, and the relationship is that this convergence in probability, this is by far the weakest one. So almost sure implies this one. P convergence, this implies LP convergence implies this one, but these ones here, that there's nothing there. This one here does not imply that, and that one here does not imply that. So that's the picture. But then there's this halfway in between with this subsequence tree. Anyway, this is a little bit advanced topic. If you are more interested in this, Richard, just maybe come to my office hours tomorrow morning, and I'm happy to talk more about this. Looking forward, what I would like to do next is introduce more martingales. So more martingales. The big class that we're ultimately going to be looking at is so the next big goal. This is to create this object here, and this is an integral. And for example, I could be interested in creating this object here. So this here is the Ito integral. So what you're noticing here is that there's a dB here. Right, so this here is absolutely not the same in any way, form or shape as this integral. It's also not the same in any possible way as something like this. This object here, this is new. And what we shall see is that it's a when I'm talking about martingales, it's not just more martingales. I should really say it's not just more martingales. It's really all martingales. And so what we're ultimately going to end up talking about is quite remarkable. We're going to be talking about a result that says, given any martingale, it's called MT. Given any martingale MT, there's a way to write MT in terms of B. When I say there is a way, I should probably be more specific here and say there is exactly one way to write this martingale. And this result we're talking about here, this is called the martingale representation theorem. And of course, martingale representation, this is a topic in stochastic analysis, a priori has nothing to do with finance. It just turns out that the martingale representation theorem, this will be how we create replicating portfolios. Remember how we did this in discrete time. Like when we created the replicating portfolio in discrete time, in the binomial model, say, we would write down these replicating equations, and there would be typically two. So there will be one equation if the next stock price would be would go up, and there'll be another one that will go down. We will solve for this delta, and we'll solve for this initial wealth, and this will be how we would create delta. Little did we know what we were doing at that point, that this is special cases of a much more general theorem, and this general theorem is martingale representation. Specific cases of the martingale representation theorem. This is what we were doing in discrete time, and now we're gonna be more specific about the shape of this theorem and how it looks like in the Brownian motion model. Okay, so how is this formed? I'm claiming that there is exactly one way to write such a martingale in terms of this Brownian motion. Okay, so how does it look like? Well, the way that it looks like is in terms of these new integrals that appear up here. These new integrals are key to go down here and do the martingale representation theorem, which is what we want to do if we want to create replicating portfolios in continuous time. So the next big object is to introduce these Ito integrals. What is the meaning with this thing? And it's not like anything we have seen before. This dBu here, this is not to be treated like a du. And why is it going to be so different? Well, maybe we should spend the rest of today's lecture. This is a big topic, right? This is going to take us a while to get all this done. This is all of chapter 4. Just to give you an idea about why is it so difficult to introduce this object here. Well, if you do, let's just compare. We compare with the Riemann integral. Right, so if I wanted to do the integral from 0 to t of Brownian motion with respect to time, but what I will do is I'll take this as a limit, and again we have this mesh, right? We had that last time, so let's just use the same notation. I'll take the mesh to go to 0, and I would be summing here over some n's, and so what would I have? I would have a time step, tn plus 1 minus tn. And so what should I put here? And so the picture is
evaluated at that value.
That's right. So I should put b, that's my integrand. And what should I put here as the subscript? If I'm looking at approximating this area here underneath that graph, maybe like, should I approximate at the left endpoint, the right endpoint, the middle point? Remember how we used the mean value theorem last time? And I think it was you, Richard, that said you're going to get the integral. That's that point that we got out, that tn star point we got out last time. Where was that point? Well,
it was the point that, yeah, we used the mean value theorem. It was like, but it was like the point that had the slope of the.
That's right. And where was the point? Well, the only thing we knew about the point was that it was somewhere in this interval. We didn't know where it would be. It would be exactly where the two slopes would be the same. But a priori, we don't know where that is. So what I'm saying is that you could choose anything you want here. You could choose the middle one, you could choose the left one, you could choose the right one. So for example, I could choose the left one up here. Or I could use the right one.
Oh, it doesn't matter because you're taking a limit, right? As they get smaller and smaller.
Or we could choose something in the middle. So now let's try to do the following. So let's now try. Let us try the E2 interval. Let's try the E2 interval. Okay, so how should we do the E2 interval? Well, let's look at BU dVU. Okay, so what should it be? It should be a limit. Right, so at this point, what we're doing is we're trying to build up intuition for what this object here, what should it be like? Well, it should be linked, it should be similar, it should be some sort of Riemann sum approximation, but instead of du over here, right, it's the du that leads us to these time differences over here. So now it's not going to be time differences, right? It's going to be Brownian motion differences because you have a dBu over here. So we could start by saying, well, maybe this should be equal to the limit as pi goes to 0, and then copy paste the formula from up there. I'll take btn. But of course, now I have a dBu here. Up here, I just have a du. So I need to change this thing to btn plus 1 minus btn. But of course, I could also equally well have chosen the limit as pi, the mesh goes to 0. And then instead of btn, I could pick the right endpoint, btn plus 1 of btn plus 1 minus btn. Or we could also chosen any other point in this interval. And so when we do the Riemann interval up here, we go down the fact that it doesn't matter. This equality sign here, this is true and this is true. They're the same. And here we have question marks. So maybe we should do a little experiment. Let's have a closer look at these approximating sums here. Okay, so how do we have a closer look? Well, we will start by computing the expectation, for example, of the right-hand side here. So we'll be summing from n equal to, say, 0, and what goes up to n minus 1. And then I'll have btn times btn plus 1 minus btn. How do we calculate what this is? Well, it's an expectation of the sum. So we could start by putting the sum outside. Start by putting the sum outside. And then what? Any ideas on how we should calculate an expectation of the random variable that's inside the sum?
Moment generating function.
Yeah, but remember it's a Brownian motion. So how does this increment here?
So it's independent, so equal to 0?
Okie dokie. So it's equal to BTN times the expectation of BTN plus 1 minus BTN. What about the other one? What about the other one? How would you do that one? So we'll have BTN now plus 1 outside. We will still put the sum outside. And then what? Right, now they're not independent anymore.
Wait, Professor, I got lost.
Yes.
What are we doing in this new step?
So when we started out with the Riemann.
Okay.
So we had a discussion about when we do the Riemann sum approximation, could we choose whatever we wanted to approximate within the interval? Right. So we could choose the left endpoint.
Mhm.
We choose the right endpoint. Nothing prevents us from choosing. We could also write limit I goes to 0. We could have chosen B, and then what could it have been? It could have been something like Tn plus 1 divided by 2.
Mhm.
We would also have done that. And no matter which one of these I would have done, you would all have been good enough to give me the left-hand side.
Okay.
So now we're trying to, I mean, ultimately what we want to do is give a definition of this object here. And I'm saying instead of just jumping ahead and giving you guys the definition, let's try to build up some intuition for why this is so complicated. And so when you start out, so this is what we want to define. And if you just look at how the Riemann integral was created, namely as limits of these Riemann sums, it seems like we could mimic the top one here by writing what I have here. I could mimic the second term by writing what I have here. And I could mimic the third one by taking the middle point here. And so my question is, we had this nice property of the Riemann integral that all of them, they give you the same.
Okay.
If you try to do the same thing for the Ito integral, so I would have these two competing with each other. Would I have the same property, namely that I get the same quantity when I take the limit? And as you can probably guess at this point, there is something fishy going on, because otherwise we wouldn't spend so much time doing this. And so we started working on the first term. If these are to be always the same, right? If I compute the expectation of each term inside here, presumably, if I want the limit to be irrelevant, I could hope that when I compute the expectation of both things, I would get the same. And so we figured out what the first one is, but we are missing the second one.
Okay.
Can we try to compute what this is? But the first term you'll get is what? It'll be BTN plus 1 squared.
Right.
What is the expectation of that thing?
That is the n plus 1.
Yes. But now what about the other one? The covariance between BTN and BTN plus 1. How would we compute that one?
Can we say these aren't independent, right?
They're not independent. But you could try to make them independent. But what could you do? You could try to write them as increments over intervals, right? So I could write the first, I could alter like the second term here. How can I alter it? I should subtract away btn and then plus btn. So then what will we get now? We'll have btn outside, and then the first part is independent. The first
And
part
second part is equal to n.
That's right. So you get that this is the sum of tn plus 1 minus tn. And what do you get here? We had that sum, I think, last time as well.
Just T big N, T capital N, telescoping sum.
That's right.
Why did that last part simplify to minus Tn?
Yeah, maybe we should fill in a few more steps here. Right, so we were interested in computing the expectation of btn times btn plus 1. That was the goal. Right? So the suggestion was, let's try to use the independence. So if I want to use the independence, I need to have increments. Okay, so if I write btn plus 1 here, I need an increment. Okay, so that will be minus btn. But now the equality sign is not true. So I need to add up the missing term, btn squared. And so now this term is independent of that term. So the expectation,
So that just goes to 0.
yeah. So you're just left here with the expectation of btn squared.
That's just a variance because the mean is 0.
Mm-hmm. Right. So this, I mean, what we have here, this is the covariance. Yeah. And so now we see the trouble. It doesn't matter. Like it doesn't matter how I choose to mesh. This is a 0 and this is Tn. I can choose to mesh however I want. I'm going to get the endpoint here and I'm going to get 0 here. So then it matters. Right? And if I choose that, I get a result that's different than when I choose this one. So do not have this property. I don't have this property up here. And it's simply just not true. This quantity and that quantity, these are different. They're not the same. So we need to make so we have a choice to make. We need to make a choice. Where should we put it? Should we use the Tn here? Should we use the Tn plus 1? Well, so then let's go back a slide. We want martingales.
Maybe the Tn.
So which of these two look like a martingale structure to you guys?
Well, if it's a martingale, the expectation is constant, right?
Yeah. So which of the two should it be?
The latter.
Well, this is
Actually, no.
no. Yeah, which one should it be?
So first, because it's constant.
Yeah, it's constant, but it's not only any constant, right? It's equal to the initial value. When you put t equal to 0, what's the left-hand side?
0.
So there's your 0.
Yeah.
So we have a choice to make. So Ito, he picks the left endpoint. There's a competing guy. His name is Stratonovich. Platonovich. He picks the middle point. This year is it's going to be this is going to give us martingales, and it's also going to give us these replicating portfolio, the hedges. So we're almost out of time. So let me spend the last couple of minutes just talking a little bit about history here. How does all this material come to be? Like, because it's kind of, there are lots of a lot of math has, like, it's made by humans, right? So there's like a side to it that maybe if you do math history, if you're in that sort of thing, then your professors will tell you about how the history is. And so I want to tell you a little bit about the history behind the E2 integral, because it's a fascinating story. So the E2 integral was developed in the 60s, and long history. Lots of famous people worked on this in the 60s and the 70s and so on. And then quite recently, early 2000s, late 90s, there was a manuscript that was discovered in Paris that was submitted by a soldier in the Second World War. And so this is the manuscript was submitted in the late 30s, early 40s. And it was submitted while the soldier was, he was at war with the Germans. He was ultimately killed. He committed suicide because he was cornered by the Germans. So he killed himself. This was in the early 40s. But while he was at war, he wrote math, and he submitted this paper. It then got lost in the war in Paris, and it wasn't until 50, 60 years later that this manuscript was developed, that was found. And at that point, in late 90s, E2 calculus was standard. Textbooks have been written, quantitative finance courses, master programs, you were already running using E2's calculus, like there were classes like this one using E2 calculus at the point. And then this manuscript is found, and inside that manuscript was E2's formula. But of course, this was written 20 years before E2 he developed his math. He didn't, of course, not to his knowledge, right? And Dublin, who did it, he was killed. And he submitted the manuscript, and he never told anybody. Like, most soldiers don't do high-end research during the Second World War, but Dublin, he did. So it's a fascinating story. There are movies made about this. So that's one way to, instead of watching Netflix and the election and all this stuff that's going on, you can also just look for the Dublin story and watch that. It's a fascinating story, and and then of course, so when you read the textbook, Steve is an honorable guy, and this textbook, I had the first versions of Steve's draft before it became a book, and there it was called E2's formula. But then this unfolded right when Steve wrote his book, and he changed it. So Steve is one of the early books to recognize this, and you can also read about the story over in the notes from Steve's perspective. So it's a fascinating story, and you'll see that our textbook called it the E2 Dublin formula. And yeah, so that's a bit of history here, and yeah, I think this is a good place to call it quits. Are there any questions before we do that? So next week, no more So we already done some intuition now, so we have to get the business and develop the theory for this stochastic integral, the E2 integral or the E2 Dublin. Ultimately, what's going to become E2's lemma and the E2 Dublin formula.
Professor, do we have enough material to solve next week's homework?
I believe so. Let me just, if I am not mistaken, I think I put only questions on there that has to do with Brownian motion. And yeah, you're all good to go. So you see that problem number 3. This is, we just did that. We just did that.
Oh, yes.
We can see B has to do with the Tn, right? And the other one is the Tn plus 1. Right. So here are the 2 expectations.
Okay.
So you should get 0 and T. I said something wrong. And yeah, so you're all good to go. You're all good to go.
Thank you.
And this question here, this one here came from a former student who was at a job interview. He came back and he was like, how do you do this? So that's no interview question. Other questions, comments? Okay, there are office hours again tomorrow morning at 9 o'clock. So remember, we changed the office hours around a little bit because my other class branched off, continuing with discrete time, and you guys are doing continuous time. So tomorrow morning from 9 to 10, there are office hours. Okay, have a good night, guys.